Hi everyone, let's talk about the trigonometric dot product. Let's say we have a couple of position vectors. Let's call this one V and another one W. And we know that the dot product of V and W, which is the same as the inner product of V and W, is equal to the sum of products of components. So if V is equal to A1, A2, all the way through to AN, and W is equal to B1, B2, all the way through to Bn, so the dimension is n, then the inner product or dot product is equal to A1, B1 plus A2, B2, all the way through to AN, Bn. But if you look at vectors like this as arrows, there's clearly something geometric going on. And the geometric aspect of this that we want to involve is the angle theta in between the two vectors. So to that end, what we're going to do is that we're going to draw the vector from the endpoint of W to the endpoint of V. And for those of you who are familiar with vectors, you'll know that this is the vector V minus W. And now we have a triangle, so we can use the cosine law. What the cosine law tells us is that the norm of V, that's its length, squared, plus the norm of W squared minus 2 times the norm of V times the norm of W times the cosine of theta is equal to the norm of V minus W squared. And now we're going to use a certain property of the inner product, which states that the norm of V squared is equal to the inner product of V with itself. So we're going to apply that to this, and that tells us that this is equal to the inner product of V minus W, comma, V minus W. And now we're going to use the distributive property of the inner product to get that this is equal to the inner product of V with V plus V with negative W plus negative W with V plus negative W with negative W. And now we can use commutativity and homogeneity on, actually first let's handle this one. So this one gives us the norm of V squared, and this one gives us the norm of W squared. And now we use homogeneity and commutativity on these two to get negative 2 V inner product W. So we've got the left and right sides of this identity. So what we can do is that we can cancel the norm of V squared on both sides, and we can cancel the norm of W squared on both sides, and we can cancel the factor of negative 2 from both sides. And what we're left with is V, the norm of V times the norm of W times the cosine of theta, which is the angle between the vectors, position vectors, is equal to the inner product of V comma W. And that is what is called the trigonometric dot product, because we have expressed the dot product or inner product in a trigonometric form involving a trigonometric function. Now there are two issues with regard to the well-definedness of the angle theta. The first one is, what if we have displacement vectors instead of position vectors? And that one is resolved because, let's say we have two parallel lines and a transversal, then if instead of two vectors coming out of the origin, we have, let's say, a displacement vector up here and a displacement vector over here. So V is over here and W is here. The thing is that we can extend their ends, one of their ends, to get an intersection point, and because of the theorem on two parallel lines and a transversal, in particular corresponding angles, we find that this angle here is well defined no matter what. So no matter which displacement vectors we take for v and w, the angle between them, theta, is well defined. So that's the first issue that we've taken care of. The second issue is that, let's say we have two vectors. The question is, what should we take theta to be over here, or should we take theta to be the other angle? And it's not clear which one we should take. But the point is that it doesn't matter, because cosine of theta is equal to the cosine of 2 pi minus theta. And you can verify this, it's a trigonometric identity. So the trigonometric dot product is well defined regardless of whether you take this as theta or this as theta. It's the same either way. Okay, thank you for watching, and I'll see you next time.